Question number 1 and question number 2 in previous parts. Okay, so here we're gonna start from question number 3a. Here it is given that state the Cauchy residue theorem. So hope you're gonna have the answer in your book, textbook, Cauchy residue theorem. Let me solve this part. Okay, only mathematical part here. Okay, so I'm gonna ignore the definitions and this statement of theorems, because these are easily available in books and in net. Okay, so let's solve this problem. Okay, so now, so here I have already written the solution. Take a screenshot and let me explain now. Here you see this is not completed in this single slide. Okay, we have more slides. So here you see, we need to prove this, right? So in order to prove this, first let us consider here that integration of dz by z square plus 1, z to the power 6 plus 1 over this contour C. Okay, and this consists this closed contour consisting of upper half of a circle CR. This is the circle CR. Here you can see this is the circle CR, and this contour C consists this upper half only this upper half, as you can see in the red color, this upper half. Okay, and also on the real axis, this is the real axis we know, and this is the imaginary axis. So on the real axis, here we have real number r, this is positive real number r, and here we have negative r, so that we can write this integral in this way. This is equal to integration from minus r to plus r. So as we are taking the real axis, so I have written here dx by x to the power 6 plus 1 and plus integration over CR. So here this part, this circumference, dz by z plus z to the power 6 plus 1. So we can write this way. Okay, and here also remember that when r tends to infinity, in that case this integration over C dz by z to the power 6 plus 1, that's going to be equal to integration from from minus r to plus r. That's going to be this, if r tends to infinity, then it's going to be minus infinity to plus infinity dx by x square plus 1. Okay, so when r tends to infinity. So as our motive is to solve the paper, that's why I'm not going to explain each and everything. So just remember these things. Okay, so what I have given, what are the informations that I have given here in order to solve this problem, those are only necessary here. So just you need to remember that I have explained now. So let me tell you again. Here you see, when you get this kind of problem, just you have to consider this. Okay, which consists of this upper half of this circle, and on the real line you have positive r to negative r. These are real numbers. And remember one thing, that as r tends to infinity, then in that case you can write integration over C dz by z square, not the square here, z to the power 6 plus 1, that's going to be equal to integration from minus infinity to plus infinity dx by x to the power 6 plus 1. These two going to be equal. Okay, and according to Cauchy residue theorem, this is going to be equal to 2 pi I sum of the residues. Okay, sum of the residues. Here we're going to get this. Okay, so we're going to use those informations. So instead of explaining each and every thing, I'm going to give you the important informations. Those are required to solve this kind of problems. Okay, so remember that for the time being. Okay, so now what I have taken here, so here you see this part, from this part what you can do, that integration over c, you can write this one as this way: z to the power 6 plus 1 1 by z to the 1 by z to the power 6 plus 1 into dz. So here this part is taken as f of z, right? Then we're gonna we have to find a pole equating the denominator is equal to 0, and here we have got z to the power 6 is equal to -1. -1 can be written in the -1 in the complex as a complex number. We can express it as -1 plus I into 0, because here you see this complex part is missing, so we can consider I into 0. So -1. So we know that cos of twice n plus 1 into pi, that's going to be -1 for n is equal to 1 to 0 1 2 3 dot 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 so on. Okay, similarly for here you know the value of sine twice n plus 1 into pi for n is equal to 0 1 2 3 dot dot dot, that's going to be equal to 0. Okay, so these are the trigonometric general solutions. Hope you know these things. Okay, if you don't know, then remember these things. Okay, these are very important. And one more thing, here you see, as we have 6 here, so we're gonna have z is equal to this whole to the power 1 by 6 on taking 6th root. Okay, and using de Moivre's theorem, what was the de Moivre's theorem? Here you see, let me write here. If you have cos theta plus I sin theta whole to the power n, then you can write cos theta by n, then you can write whole to the power n, then you can write cos n theta plus I sin n theta. You can write this way. This is the de Moivre's theorem. And as we have here 1 by n, so it's going to be theta by n on removing this power. Okay, here also theta by n. So hope you have understood this. So instead of n, we have 6 here, so that's why we have got those values, right? So here you see, let's put n is equal to 0 to get the pole, first pole. Okay, as we have z to the power 6, that's why there must be 6 poles. But okay, let's find 6 poles here. You see, let's put n is equal to 0. Then we're gonna get, after putting 0 here, we're gonna get z1. Z1 means we have taken for the value of z on putting n is equal to 0. Right, on putting n is equal to 0, whatever the value of the z we have got, we have taken that one as z1, and next one will be taken as z2. Okay, so on putting n is equal to 0, we have got this, which also can be written in this form, right? E to the power I pi by 6. Remember that. So if you have cos theta plus I sin theta, then it also can be written as e to the power I theta. Okay, so this is very important information. Just remember this, okay, for the time being. So now you see, similarly we have found a value of cos pi by 6 and sin pi by 6, and we have put those values. Then e to the power I pi by 6 will be equal to root 3 by 2 and I into half, right? So similarly, we have put n is equal to 1, n is equal to 2, and n is equal to 3, n is equal to 4, n is equal to 5 in order to obtain z2, z3, z4 and z5, okay, and z6 as well. But here you can see, if you observe those values, let me clean this things a little bit. Okay, if you observe those values here, you see, just wait. Here this part is positive, and here also it is positive. Here you can see the imaginary part, and here also imaginary part is positive. But here you see, in these three results, e to the power I7. Now here you see, in these three results, this 3 here, you see e to the power 7 pi by 6, that is equal to minus root 3 by 2 minus I half. So here imaginary part is negative, and in the next one also, in the next pole, e to the power I 3 pi by 2, here also it is minus I, and here e to the power I 11 pi by 6, that is also equal to this, where imaginary part is negative. So now you see, according to our consideration, so we are taking the closed contour consisting upper half, here you can say this upper half, this part, this upper half, and real axis from minus to plus r, real axis minus to plus r. So I have taken only we have taken only this part, as you can see clearly. Let me use another color here. So this part, right, so shown by black color, only this part. So here you see this is the imaginary axis, and the below the real axis, this part is negative. Okay, this part is negative, which is not included in the region that we are considering here. Okay, so hope you have understood, which is outside C, right? So here these 3 poles are outside C, so we're gonna take only first 3 poles, that those are Z1, Z2 and Z3, right? Just wait, let me clean it so that you can take the screenshot. So here you see that take the screenshot here. You see we have put n is equal to 0, n is equal to 1, 2, 3, 4, 5 to get the poles Z1, Z2, Z3, Z4, Z5 and here Z6. Okay, so out of those 6, these 3 are outside C, so that's why we are not going to consider those. Now let me go to the next slide. Here you see, so what are the poles? These are the 3 poles we are getting here. Then by Cauchy's residue theorem we can write this. Okay, this is equation number 1, suppose. So sum of the residues, let us find the residue. How to find the residue? Residue at Z1, that means Z is equal to Z1, Z is equal to Z1, which is equal to this is the Z1, right? Either you can write this one or you can write this one, both are Z1. Okay, so now you see, let me clean it. Now how to find the residue? In order to find the residue, we used to follow this formula. So here you see this these poles are of order 1, right? So poles of order 1. So in case of poles of order 1, if suppose Z is equal to A is a pole of order 1, then we need to find the residue at Z is equal to A, suppose. Then what we used to do, we used to take limit Z tends to A, then Z minus A into f of Z, right? Here f of Z is this one, f of Z is equal to nothing but this one, right? Sorry, f of Z is equal to here 1 by Z to the power 6 plus 1, and this one into this one can be written this way, right? So now you see, here you see, as Z1 is a pole of this, right? Z1 is a pole of f of Z, so that's why if you put Z1 here, then it must give you 0, because we used to determine the pole taking denominator is equal to 0, right? That's why if you put the pole here, then you're gonna get definitely 0. So that's why what we're gonna do in this case, we can here you see, in this case we're gonna apply the L Hospital's rule. What is that rule? So suppose if you have a limit Z tends to A, here f of Z by suppose Z of Z, two different functions, and for Z is equal to A, if G of Z becomes 0, then what we're going to take? We're going to take limit Z tends to A, and we're going to take derivative of f of Z, and derivative of g of z. So if you apply that rule here, then you have to differentiate this and this with respect to z, right? If you differentiate this numerator with respect to z, you're gonna get 1 because we are differentiating with respect to z. So derivative of z1, that's gonna be 0, derivative of z will be 1, and derivative of this part gonna be 6z to the power 5, right? And this can be written, and now you see, using this limit z tends to z1, we can write 1 by 6 z1 to the power 5, which can be written as 1 by 6 z1 to the power minus 5, right? And z1 is nothing but, you can put this, z1 is equal to e to the power I pi by 6. You can put that, and putting that we have got this. Now you see, you can write this one in this form as well. E to the power, you see, let me tell you one thing. E to the power I theta is equal to cos theta plus I sin theta, right? If you use that, then you're gonna get this. If you have e to the power minus I sin theta, then this sign gonna be minus. Yeah, it's gonna be minus, right? So hope you have understood this. So that's what we have applied. Then I hope you can evaluate these trigonometric ratios, values of these trigonometric ratios, and then you're gonna get this value. Similarly, we have find residue at z is equal to z2, at z is equal to z2. Again, applying L'Hospital rule, we have got this, and then again putting z2 is equal to this value. Here you see, this is the z2, right? Then we have got this one. So similarly, we have found the residue at z3, and let me clean this. So we have got the 3 residues, this one, and this one. So here we need to put the sum of the residues, right? So let us put this residue here. Let us sum up this residue and put here in equation number 1. So let me go to the next slide. So here you see, from 1 we can write this one is equal to 2 pi I sum of the residues. Okay, if you put the residues here, and these two cancels, here you see these two cancels, and after simplification we have got this value. As I have already told you that as r tends to infinity, then you can write this one is equal to this one, right? Here this one minus infinity to plus infinity, then it's gonna be equal to this one, right? So we have got this, and we have got the value of this here, 2 pi by 3. Then here you see this is even function, so you can write, instead of writing in case of even function, minus a to plus a f of z dz, it can be written this way, 0 to a to f of z dz. So applying that, we have got this, right? And these two cancels. So hope you have understood this. So let me show you, let me play this slide, how I have done this. Let me show you. So here you see, this is the last slide I'm playing here, so that you can understand what I have done here. So I have put the residues, and I have cancelled what are the terms to be cancelled out. So that's how we have got this value, 2 pi by 3, as r tends to infinity. So we're gonna get this result, and 2 pi by 3, so it can be written this way, then 2 cancels, we're gonna get this result. So hope you have understood this. So this is what we needed to prove, right? So hope you have understood this. So let's move on to next question. So now let us solve question number 3b. So here you see this function f of z u plus iv is analytic, and u is equal to this one. We need to prove that u is harmonic, and also we need to find the value of v. So let me go to the solution part. Here you see this is the solution, and here you see it is given this is analytic, and we need to show that u is harmonic, and to be harmonic u must satisfy this condition: second order partial derivative of u with respect to x plus second order partial derivative of u with respect to y, that must be equal to 0. And also value of u is given here. So let us find partial derivative of u with respect to x first. So here what I have done here, I have applied u into v rule here. So first function, this is e to the power minus x, then derivative of the second function. Okay, so derivative of x, that's gonna be 1, and this is function of u that should be taken as constant, as function of y that should be taken as constant, because we are differentiating here x. Then this part is completely function of y, so that's gonna be 0. Then again, then second function, this is the second function, derivative of this, that's gonna be minus e to the power x, so that's why this minus comes here. So hope you have understood. So what rule I have applied here? This product rule of derivative, that is u into v rule, derivative of this u, derivative of v plus v, derivative of u. I have applied this one, right? So hope you have understood. Similarly, if you differentiate it again, then you're gonna get this result, right? Similarly, you can differentiate u with respect to y as well, and if you differentiate it again, if you find a second order partial derivative, then you're gonna get this result, right? So now let us check the left hand side of this result. Now let us add the second order partial derivative of u with respect to x, and second order partial derivative of u with respect to y. If the sum is 0, then we can say that u is harmonic. So here I have added these two results. So here this e to the power minus x is taken common, and remaining parts are written in this within this bracket, and those terms which are cancelled out, I have cancelled here. Then I have got here 0. As I have got 0 here, so u is harmonic. Okay, so let me play this slide once. Okay, just wait, give me a second, just wait, let me clean it first. Okay, so here let me play this slide. So hope you're gonna take the screenshot. So conditions to be harmonic, this is the conditions to be harmonic. So let me play the slide here. So this is the condition that is satisfied, so these terms are cancelled, right? So now let us find the value of v. Now let us find v. Okay, now let me go to the new slide so that I can show you how to find v. So here you see, so this is how I have found v. So this function is analytic. If this is the analytic function, then what are the then it must satisfy these conditions, CR conditions, to be analytic, Cauchy-Riemann conditions that we have already discussed in complex variable, right? So these are the conditions, right? And complete differentiation of this v, dv is given by this, can be written this way. And here you see, so as we need to find v, and we know the results of del u by del x, del u by del y. So that's why, so del v by del x is replaced by del u by del x is replaced by this minus can be written here. If you make it positive, then it will be negative. So we can replace this one by minus del u by del y, then del v by del y. So I have replaced this one, del u by del x, I have replaced this del v by del y by del u by del x from this relation. Here you can see, just wait. So del v by del y is equal to del u by del x. So this is replaced by del u by del x. So hope you have understood this. So now you see, if you use the results of del u by del y, then you're gonna get this, as we have got in previous slide. Let me go back to the previous slide. Here you see, this is del u by del y and this is del u by del x. These two results are used here. Okay, del u by del x, del u by del y, these results are used here, and simplifying this, we have got this result, right? Next step. So here you see, if you observe the terms which are underlined with the same color, by the same color. Here you see. So if you these three terms can be written as derivative of this product of these three, because if you differentiate, let me just clean this. If you differentiate it with respect to x, then derivative of e to the power minus x first function is this one. Then I have written the remaining functions. Then plus derivative of second function, that is x, that's gonna be 1. Then the remaining functions are e to the power minus x and cos y. Then derivative of cos y, that's gonna be minus sin y, right? So here, that's why I have written here minus, because it is function of y, we are differentiating with respect to x, so there must be a dy by dx after that, right? So this gonna imply that d of this derivative of this part is equal to this, right? So hope you have understood this. If you multiply both sides by dx, then you're gonna get this, right? So hope you have understood. Similarly, if you see that derivative of this one, its result gonna be this one plus this one and this one, right? You can check yourself, right? So here you can see that I have shown how I have obtained this part. Okay, if you differentiate this, here I have shown here, if you differentiate this, then you're gonna get this one. So this is nothing but sum of this one and this one, right? You can check yourself, right? Similarly, sum of these three terms, this one and this one, is nothing but derivative of this e to the power minus x into y into sin y, right? And now if you integrate both sides, so let me clean it. If you integrate both sides, then you're gonna get this result. This is the integrating constant and this is the value of p. That's how we can obtain the result, obtain the value of p. So hope you have understood. Now let's move on to next question. Now let us solve question number 3c. This is 3c. So here, state Cauchy integral formula for derivative of a function. So these things are already discussed in complex variables. So hope you watch the lectures on complex variables. Okay, if you haven't watched those lectures, then please check the playlist. Now we are going to evaluate only this part here. I'm going to show you how to evaluate this part only. Okay, I'm not going to write the answers where those statements of theorems and definitions in this paper. Okay, because you're gonna get those in books. So now let's solve it. So we need to evaluate this integral, right? So where c is the circle, mod of z is equal to 3, that means radius is 3 here, and center is o, origin is the center, right? So let's solve it. So here is the solution of 3c, right? This is the circle, given circle. So let us take f of z is equal to this one. So this is our function of complex variable. So equating the denominator to 0, then we're gonna get the pole. So as we have power 4 here, so it's gonna be the pole of order 4, z is equal to minus 1. So if it is the pole of order 4, then residue at f of z at residue of f of z at z is equal to minus 1. So now for the pole of order n, we know how to find the residue. Residue at z is equal to, suppose a, which is suppose pole of order n. If that is the pole of order n, then what we used to do, we used to take limit z tends to a, then z minus a. So just wait, in case of here you see, this is order is n, so here z minus a to the power n. Then I have missed one thing, that is what, just wait, let me got it. So then here n factorial should be there. Okay, sorry, not n factorial, for nth order n minus 1 factorial should be there, 1 should be less. So that's why here you see this is order of 4, so that's why I am taking here n 4 minus 1 factorial. Then for nth order you have to take n minus 1 order derivative, that means dn minus 1 here, z dz n minus 1, so n minus 1 order derivative, so that's why I have taken here third order derivative when the order is 4. Order of pole of order 4, in order to find a residue at pole of order 4 you have to take third order derivative, right? The order of the derivative is 1 less than the order of the pole, just remember that. Then what to do, then here you need to multiply z minus a whole to the power n. So here as we have minus 1 here, so I am taking plus 1 whole to the power 4 order 4 nth order, that should be 1, but here it is order 4. Then f of z, this is f of z, okay, that is what we have applied. So hope you have understood this. Let me write this one again, just wait. So what formula that I have applied here, that is residue at pole z is equal to a of order n is given by limit z tends to a 1 by n minus 1 factorial, then z minus a. If this is negative, this is positive, then there should be negative. If this is negative, then that should be positive. Hope you have understood this. So nth order, so that should be n. Then just wait, n minus 1 order derivative, n minus 1 order derivative with respect to z, then here f of z. So this is used here, right? So now these two cancel, so we have this one only. So now let us differentiate this. So if you differentiate, I have shown the differentiation here, okay. So if you differentiate this one with respect to z once, then you're gonna get this, okay, 2e to the power 2z. If you differentiate it again, then it's gonna be 4e to the power 2z, and if you differentiate it again, that means if you find a third order derivative, then 8 into e to the power 2z. That's what we have got here, right? So this 8 is cancelled by this 6. 8 and 6 both are cancelled by 2. 2 4s are 8, 2 3s are 6, right? So hope you have understood this. Then we have got here 4 by 3 e to the power minus 2. As z tends to minus 1, I have put here minus 1. So that's why we have got minus 2 here, and that's why it is the result. This is the residue I have got. So by Cauchy's residue theorem, so this integral must be equal to 2 pi into sum of the residue. As we have got only one residue here, that should be put here, that should be written here, and doing so we have got this result. This is the result. So hope you have understood this. So now take a screenshot. Let me clean this first, so then kindly take a screenshot here. Just wait. Okay, just wait. So now you can take a screenshot. Okay. So now let's move on to next question number 3D. Okay, so this is the question number 3D. We need to find the residue of this. Okay, so it's very simple, you know already how to find residue. Let's go to the solution. So here is the 3D solution. So in order to find in order to find the residue, we need to know the poles. So that's why that can be obtained by equating the denominator to 0. That's what I have done here. So here you see, as we have power 2 here, that's why z minus 1 is a order of pole of order 2, and here we have power 1. So that's why z is equal to plus minus 2i, that is a pole of order 1, right? So as I have already told you, now how to find the residue depending on the order. So here it is order 2, so that's why here z plus 1 whole to the power 2, z tends to minus 1, and this is order for nth order, here n minus 1, so it is second order, so that should be 2 minus 1. And for second order, the order of the derivative should be 1 less, that is first order derivative. And this is our fz, right? So hope you have understood this. Now differentiate and simplify these things. Then we have got the residue at z is equal to minus 1. We have got this residue. Okay, similarly we have got the residue at z is equal to 2i is equal to, so I have written, I think, on the other side. So again I have applied the same formula that I have already told you, that residue at z is equal to a, which is suppose nth order pole. In that case, then limit z tends to a, then 1 by n minus 1 factorial, 1 by n minus 1 factorial, this order of the derivative should be 1 less than the order of the pole, that is n minus 1th order. Then here as z tends to a, so we should take z minus a for nth order, their power should be n, then f of z. So we have applied this formula right here also, and doing so what we have got, so here you see this is the residue at 2i, and similarly we have got residue at minus 2i, this one, right? This is the residue at minus 2i. So we have got all the three residues, this one, and go back to previous slide, this one. These are the three residue we needed to find. So now let's move on to the next problem, that is question number 3. So here is the question number 3e. So find the Laurent series of this about z is equal to 1. So let me go to the solution. Here is the solution of 3e. This is the function f of z, right? We need to find the Laurent series about this. First, remember this result, e to the power x is equal to 1 plus x square by 2 factorial into plus x cube by 3 factorial, and so on, dot, right? So here we have taken z minus 1 as u for simplicity, z is equal to u plus 1, and if you replace the z by this value, then this function f of z becomes this, right? So from here what you can do, you can write e to the power 2u plus 1, it can be written this way, e to the power 2u plus 2, which is going to give you e to the power 2u into e to the power 2. That is what we have got here, right? So hope you have understood this. Then let us expand this part using this result. So we have got this, right? So now here you see what we can do. This part within bracket, this can be written using summation. So from n is equal to 0 to infinity, right? 1 by n factorial, okay, 2u to the power n. If you put n is equal to 0, 1 to 3, then you're gonna get this series again, right? So hope you have understood this. So then it can be simplified this way, right? Now you see here what I have done here, I have divided this one by this part, and doing so I have got this result, right? So hope you have understood. So now what we can do here, again I have expanded this summation in this way. This is the expansion, and then here you see, just wait, let me explain one or two terms that I have got. So first what I have done, I have put 0 here, factorial 0 will be 1, then 2 to the power 0, that's going to be 1, then here you're going to get 0 here, that is u to the power minus 3, that's a u to the power minus 3, that is 1 by u to the power 3, right? That's how we have got. Then we have put 1, factorial 1 is also 1, then here 2 to the power 1 is 2, this is the 2 here, you can see, this is the 2. Then if you put here 1, then u to the power minus 2, u to the power minus 2, that's why u to the power minus 2, that's going to be 1 by u square. As we on putting 1 here, we have got 2, so 2 by this, and that's how we have got the remaining terms as well on putting n is equal to 0, 1, 2, 3, dot, so on, and e to the power 2 is taken common from all the terms, okay? Then replace this u by z minus 1 that we have considered here. So doing so, we have got this series. So this is the required series. So hope you have understood this, and remaining questions will be solved in the next video. So thank you for watching. See you in the next video. Share the video with your friends and hit the thumbs up button. Okay, so see you in the next video. Bye bye.